Okay, now we're going to talk about how you make an actual review for this so that you know what to do. I have lots of crayons and markers and all kinds of fun things, and I want to use those in order to create our review. The first thing that I'm going to do, though, is I'm going to go back and I'm going to reference what we're supposed to know. So remember that concept tracker that you guys never look at? If you ever look at it, it will actually tell you exactly what you're going to be tested on next. So the very first thing we have here is Bernoulli's principle. You should have done the Edpuzzle for that already. And then down here we have an entire topic called fluid systems, open versus closed, hydraulic versus pneumatic, distance multipliers, force multipliers, velocity, and resistance. So all of these things are available for you right here. You should all have them in your files at this point in time. The first thing that I'm going to do after this is actually go back and make myself a study guide. I like to make study guides in your notebooks, actually. So for argument's sake, what I'm going to do is I'm going to make it on a very large piece of paper and try and write big enough so that you can all see. A great way to go about doing this is actually to fold yourself into a little margin so that you can start to quiz yourself. There are also a ton of definitions on Quizlet, so if you want to make sure that you do that and study while you're coming to school or while you're on your way home from school, that is also a really good idea because that will show you and that will help you make sure that you know all of your definitions. And that's a lot of this unit in particular is just knowing, like, when I say things in nerd, you understand what I'm saying. That said, if you just take your notebook paper and you fold it over so you leave yourself a little margin, then what I find I have to do is make a little line. I'm going to do it in a light color so that it doesn't really, make a huge mess. But you see here, I've just gone and I've made it in yellow. So now when I open this up, I have this line right here. And your natural lines on your notebook is always a really good thing to use too as a guide. So the very first thing that I'm going to do is spin this around so that you can see what I am writing. And I've said the first thing about 5 times now, so clearly this I think is the 5th thing that I'm doing. I want to start here with open versus closed. And what I'm going to do is say, all right, I have some systems. Can you see this? Open versus closed. Okay. And what we're going to do is basically just fill it in. I don't think it's necessary for me to do all of this, so I'm not going to. Right here, what you're going to do is go back and say an open system is... and you can fill that in. A closed system. And a really good thing to do here is actually put in examples. So that is really important. And you can say examples so that you know what those are and how we apply them. So this is where we apply these definitions. And we used closed systems in our robots. So you have a great example of a closed system already. All right, so that is concept 12, open versus closed systems. The next thing is hydraulic versus pneumatic. Now, we have really beaten that one into the ground. I feel like everyone should get that one correct. And if you don't, I might be kind of disappointed. So please make sure that you know. Hydraulic versus pneumatic. And remember, pneumatic, of course, starts with a P. Hydraulic versus pneumatic systems. And again, you want to come back over here and in your study guide, write, a hydraulic system is, and you fill that in, a pneumatic system is, and again, very important that you have examples of each. I saw many of you saying car was an example of a hydraulic or a pneumatic. Please be very careful. Car brakes are hydraulic, but the entire car itself is not. So car brakes are very nice because they're immediately responding, and that is the power of a hydraulic system. It's also incompressible, so you will get some immediate reaction. Okay, excellent. The next thing, hydraulic versus pneumatic, distance and force multipliers. Now that was something that we briefly defined. It is something that we were creating. We were creating some force multipliers and direction changers. We did not have a chance to do much with distance multipliers, although if you did use two different sizes of syringes, you were using a distance multiplier because you were changing the distance that something went somewhere else, and that's what's cool about that. So, distance and force multipliers. Oops, I spelled it wrong. Multipliers. All right, again, you go back here and you put in your definition. A distance multiplier is a force multiplier is. Okay, and again, super important, examples. How do we apply these things in real life? Now, if you haven't played with this yet, look how cool this is. This is how your study guide works, and if it's in your notebook, it's even better. Now, what you do is, when you don't write in pen, oh, actually, don't use Sharpie, clearly it's leaking through. What you do is you go back and you say, oh, here, now I can start to quiz myself, and look under this little flap, and it will show me what the correct answer is, and I can start to test myself without having to be in front of the computer, which is great. The next concept that we need to know is fluid motion, all right? And we're talking about velocity. Recognize the velocity of a liquid in a moving pipe varies inversely with changes in the cross-sectional area of the pipe. What does that mean? I just went over that in the last video, but I will go over it again because I think this is really important. So, fluid resistance. I'm sorry, fluid velocity. All right. The velocity of the fluid moving in a pipe. And again, velocity is nerd for speed. Okay. Velocity of a fluid, whoopsies, speeds up, so it will go faster in a wider pipe. I'm sorry, that's wrong. It will flow slower. So when you make the pipe very wide, it will flow slower. It will flow faster in a pipe with a smaller cross-sectional area. And some of you saw, I'm sure, the writing over here. And I like to use this. So let's draw some graphics here. What this says is, and I'm going to call fluid velocity a script V. All right, that's what velocity is going to be known as. So I'm going to use that symbol right there to represent the velocity in this conversation. And the area, your cross-sectional area, we have done area several times. We represent it with a capital A. All right, and we're talking about pipes, so most of the time it's going to be talking about something that's circular. We're not going to worry about calculating that size, but the area is the width. When you have a small velocity, what that means is your area of your pipe, your cross-sectional area, must be very large to allow it to flow smoothly and slowly. At the same time, when you make your area smaller by putting your thumb over a hose, you make your area much smaller. What happens is you end up with a much faster spray of water. So when your area is smaller, that means that you must have a much bigger velocity. Okay? We can also take a look at this as a table. So we have our velocity and how it relates to our area. And what we can say is when our velocity increases, our area must be decreasing. That's what this says right here. That's how that's summarized. At the same time, when our velocity decreases, that means that our area must be increasing. This is an opposite relationship. It's actually called an inverse. So when one thing happens to one side, the opposite happens to the other. Okay? So let's hang on to that. I think that I might pause right now and go on to a different video. So I'm going to stop that and we'll start a new one so that you don't have to go through all of it to find what you're looking for.